Hello everyone, I'm Marios and welcome on our second class of Principles of Lights. Today's lessons will be about two-dimensional airflow around an aerofoil. As we can see here, it has 56 questions and again we are going to pick up 30. So let's get started. Where would you expect the forward stagnation point of an aerofoil to be during slow flight? Let's begin with the most common and used formula for principal flights. Lift equals 1/2 rho v squared s cl. If you want to keep the lift constant and be straight and level in a slow flight, for example, to we must degree v squared, we must increase the cl, the coefficient of lift. This is, and we increase the coefficient of lift by increasing the angle of attack alpha. Stagnation point is a point right here where the relative airflow of the wind hits the airfoil at 90 degrees angle of attack and is 0. So slow flight our airfoil will be something like this, and now our stagnation point moves downward, because to increase our CL we have to increase our angle of attack. Sorry for this diagram, but you have to see it for a reminder. So we expect the stagnation point to move to the lower surface of the airfoil, so it's here, lower surface. Comparing the lift coefficient and drag coefficient for conventional airplanes, coefficient of lift is lower than coefficient of drag, coefficient of lift is much greater than coefficient of drag. Of course, this is correct. Coefficient of lift is much lower than coefficient of drag, and coefficient of lift has approximately the same value as coefficient of drag. Of course, the correct answer is coefficient of lift is much greater than coefficient of drag. Which of these statements about a steady subsonic flow are correct or incorrect? The static pressure decreases as the streamlines diverge. Of course, this is incorrect. And the velocity increases as the streamlines diverge. Of course, this is incorrect. Let's go. Again, let's draw our Venturi tube. This is the undisturbed airflow, and moreover we're going to keep this figure. I suppose we are going to need this for next questions. As you can see here, oops, inside the throat the lines will diverge in order to keep the mass flow constant according to Bernoulli's theorem. According to theorem of continuity, and as they get the bigger area, the lines diverge, and when the lines diverge, the velocity decreases. And the pressure total here must be equal with pressure total here, and must be equal with the pressure total here. It is pressure static plus dynamic pressure to pressure static 1 plus Q1, and in order to remain this constant, this has to go down because speed goes up, dynamic pressure goes up, and the formula of dynamic pressure 1/2 rho v squared. And at this point, pressure static 3 goes up because dynamic pressure goes down. So the static pressure decreases as the streamlines diverge. Here the streamlines diverge and the pressure static increases, does not increase, so this is incorrect. And the velocity increases. No, both of them are incorrect. What will refer to the figure? What will be the consequence on the speed of the aircraft while going from point B to point C and maintaining steady, straight and level flight from point B to point C? B to point C. As you can see here, we are increasing our coefficient of lift and angle of attack, but we want to remain in straight level flight. So, of course, I'm going to keep the Venturi tube. Again, we are going to use our lift equation. Lift equals 1/2 rho v squared s CL. If we want to keep this constant and we increase coefficient of lift, speed must go down. Of course, we are talking say remaining on the same level, so we cannot change density, and of course nothing about changing the area, for example configuration. We're not changing configuration. So let's see the possible answers. The aircraft will be flown at a slower speed. Obviously, this is the correct answer. Let's see also the rest of them. The aircraft will be flown at a faster speed. Of course, no. The aircraft speed remains unchanged. The aircraft will stall. No. It would be stalled if we were at this point. But at point C, we have achieved the CL max, coefficient of lift max. Considering the airflow around a positively cambered airfoil that is producing lift, the point of minimum static pressure is found at the point where the chord line originates from the leading edge, where the streamlines are closest together, slightly below the point at which the chord line originates from the leading edge, and at the point of maximum camber on the upper surface. These B and D are sounds more correct, but let's draw the picture. This is the chord line, something like the chord line. The relative airflow. We know from our theory when the streamlines diverge and come closer together means that speed increases. So the point where the streamlines are the closest together, pressure total equals with pressure static and Q. When the streamlines are the closest together, dynamic pressure hits the highest value. Also, static pressure hits the lower value. So where the streamlines are closest together, this is the correct answer B. When flying in icing conditions, ice buildup on an airfoil will usually occur in the area of the stagnation point, close to the center of pressure, close to the trailing edge, or on upper surface from the leading to the trailing edge. Icing conditions will happen at the stagnation point because at the stagnation point velocity is zero. So you can imagine it as the water stacks at this point because the water at this point on every of these points is taken away from the wind, but at this point the water is stuck and cannot leave, so icing occurs. So it's in the area of the stagnation point. Stagnation point moves up. What is the cause? if we increase our angle of attack, we see that stagnation point moves down. But if we lower our angle of attack, decrease our shell, our coefficient of lift, the point where the relative airflow hits at the exact point which the velocity is 0 moves up. So we have a negative angle of attack right here. Excuse me. Lower angle of attack, decrease, lower angle of attack. Excuse me. The rest of the answers were higher angle of attack. Of course, no, because at higher angle of attack, the stagnation point will move to the lower surface of the aerofoil, eyes on the leading edge, no, and decreasing flap settings. No. Based on the two-dimensional drag formula, drag is, let's draw the drag, the formula of drag. One half rho b squared s coefficient of drag. So proportional to the square root of the speed, of course. Proportional to the square of the speed. No, this is wrong. Square root. Okay. Proportional. You see, guys, don't do my mistake. Proportional to the square of the speed, inversely proportional to the speed, and proportional to speed. It is proportional to the square of the speed, according to our formula. I was going too fast and I was ready to press A, but no, it's B. We must be very careful because it may seem easy sometimes and we may get tricked. Assuming all bodies have the same cross-sectional area and are in motion, which body will have the highest form of drag? Okay, of course, you see here 3 and 4 that are somehow curved and way smoother than A and 2, or that 1 and 2. So we also can see some kind of curvedness here. So the highest form of drag will be on this flat plate, number 2. An aircraft is flying straight and level, assuming there are no mechanical malfunctions or environmental errors affecting the indicator. What can be said to remain constant if the speed indicated in the airspeed indicator does not change? The dynamic pressure, the temperature, the true airspeed, and the air density. In our aircraft, we have our instrument, which is called instrument airspeed indicator receives dynamic pressure from instrument which is called pitot. Pitot measures dynamic pressure. This is how we get our airspeed. So the correct answer here is dynamic pressure. Select the correct statement in regard to a steady subsonic flow. Velocity increases as streamline converts. This is totally true. Let's see also the rest of them. Static pressure increases as streamlines converts. Wrong. Static pressure does not change as streamlines converts. Wrong. And velocity does not change as this. Okay. Let's go here. Velocity increases as streamline converts. Streamlines converge, then velocity increases, dynamic pressure goes up, pressure static goes down. An airplane in straight and level flight is subjected to a strong vertical gust. The point on the wing where the instantaneous variation in a wing lift effectively acts is known as the aerodynamic. According to our theory, this point is the aerodynamic center of the wing. During a straight and level flight, the pilot eases back on the control column to gain altitude. What effect will this have on the stagnation point of the airfoil and the angle of attack? The leading edge stagnation point of the airfoil moves towards. Let's draw the picture. He pull he pulls the yoke back, so he wants to increase the coefficient of lift. He wants to increase the angle of attack. So I can do better than that. The stagnation point moves to the lower surface. Moreover, the angle of attack increases. The leading edge of the stagnation point of the airfoil moves towards the lower, and the angle of attack increases. So the correct answer is A. The location of the wing center of pressure, forward, off, or aft of the center of gravity, influences the pitching moment, but it does not affect the magnitude of the stabilizer balancing force, pitching moment, and consequently the direction of the stabilizer balancing force. Okay, this one is correct, but let's see why. This is most of, let's say, performance, let's say, mass and balance, excuse me, question, but let's draw our balance arm. Oh, no, I want also our center of gravity, our lift, this is the downforce of the tail plane. Center of pressure, let's say 3, center of pressure 2, and center of pressure 1. We have here the downforce of the tail plane. This is called balance R. We have here the center of pressure, the center of gravity, and the downforce. Center of pressure gives a pitching moment like this, but it is counteracted by the downforce, which gives a pitching moment like this and rotates around the center of gravity of the aircraft. If we decrease the distance from the center of gravity and the center of pressure, we also have this pitching moment from the center of pressure, but it is not so strong enough. So we must reduce the downforce in order to be able to maintain this straight and level flight. But if the center of pressure moves forward of the center of gravity, it has a pitching moment like this around the center of gravity, and the downforce now has to move like this in order to counteract this pitching moment. So the location of the wing center of pressure, forward or aft of the center of gravity, influences the pitching moment and consequently the direction of the stabilizer balancing force. From the following, select a graph or graphs that represent an airfoil with negative camber. So in this graph, we see the coefficient of lift on the y-axis, the alpha, the angle of attack, on the x-axis. So airfoil number 2, it seems like a symmetrical airfoil. Airfoil number 1, you see even at zero angle of attack, it produces lift. So it is obviously a positively cambered airfoil, and airfoil number 3, even if it has a plus 4 degrees of angle of attack, it produces no lift. So it has obviously a negative camber. So it's obviously a negative camber airfoil. So the correct answer is 3. 3 only. Consider the coefficient of lift versus angle of attack graph of a non-symmetrical airfoil with the x-axis representing angle of attack and y-axis representing coefficient of lift. The angle of attack at which the airfoil achieves coefficient of lift max can be found on the graph. Very easy, this is pretty straightforward. Let's draw here the y-axis. Okay, easy. The y-axis, coefficient of lift, alpha. We can see here coefficient of lift increases up to a point that we achieve coefficient of max and then drops suddenly. This point, oops, the point right here is where we have coefficient of lift max at this angle of attack. If we increase further the angle of attack, we will stall. It's also called critical alpha. So, at the point where it crosses the x-axis, no. At its highest x value, no. At the point where it crosses the y-axis, at its highest y value. It is at its highest y value. You see it here. At its highest y value, this is the y-axis, and this is the x-axis. Assuming no flow separation, which of these statements about the flow around an aerofoil as the angle of attack decreases are correct or incorrect? The stagnation point moves down, angle of attack decreases. The stagnation point on the airfoil is right here, and this airfoil it's somewhere here. So the stagnation point moves up. The point of the lowest static pressure moves forward. The point of the lowest static pressure moves forward. Here the lowest increase. The point of the lower static pressure moves backwards. So if we increase, let's say, like that. As we increase the angle of attack, the lines converge here. And speed increases at this point. But if we decrease our angle of attack on this airfoil, the point of the lowest static pressure that we are going to have the highest dynamic pressure moves backwards. So backwards number 2 is incorrect and number 1 is also incorrect. Both are incorrect. Considering the airflow around a positively cambered airfoil that is producing lift, the point of minimum static pressure is found at the point where the chord line originates from the leading edge, slightly below the point at which the chord line originates from the leading edge, at the point of maximum camber of the upper surface, at the highest speed. Of course, is answer number D, because total pressure at all points must remain constant, pressure static and Q, and at the highest Q have the lowest static pressure. So you have the lowest static pressure, so it's at the highest speed. Typically, the coefficient of lift to coefficient of drag ratio is maximum at an angle of attack of 16 degrees, minimum, okay. According to our theory, coefficient of lift to coefficient of drag ratio is maximum at an angle of attack of 4 degrees, according to our theory. At a constant airspeed, a reduction in an airfoil's angle of attack results in the speed of the flow over the upper surface to a reduction in the angle of attack. Decrease, decrease. Constant airspeed. Decrease and the lifting ability of the airfoils to decrease. Increase and the lifting ability of the airfoil to increase. Decrease and the lifting ability of the airfoil to increase. Increase and the lifting ability of the airfoil to decrease. So when we increase the angle of attack, we know that air here has to travel faster to keep up in pace with these streamlines. So when we decrease, things change. When we decrease our angle of attack, so speed decreases on the upper surface and lift capability decreases because pressure differential is not as high as at this point, as at this airfoil. So on the upper airfoil, decrease, decrease. Decrease, and the lifting ability of the airfoil decrease. Easy. The aerodynamic center of the wing is the point where, pure theory, the airplane's lateral axis intersects with the center of gravity. The pitching moment coefficient does not vary with angle of attack. Changes of lift due to variation in angle of attack are constant, and aerodynamic forces are constant. The pitching moment coefficient does not vary with angle of attack. This is theory. 2 points are marked on the wing, V1 and V2, given on air velocity of V. Select the correct option. Here we can see a positively cambered airfoil. It has some kind of angle of attack. Of course, V2 is higher speed than V1, which is a stagnation point. And I cannot find V. Okay, so where is V? So V1 is 0 and V2 is, okay, V is the undisturbed airflow. So V1 is 0, of course. V, it should be something like V over here, with this, which is the speed of the undisturbed airflow, and due to the curvedness and the angle of attack of the airfoil, V2 is higher than V2, and V1 is the stagnation point where V1 is 0. So V1 is 0 and V2 higher than V. The lift force acting on an airfoil is mainly caused by reduced pressure on the upper surface. That sounds perfect. Is mainly caused by overpressure on the underside of the airfoil. No. Increases proportional to the angle of attack until 4 degrees. 4 degrees is huge. Is maximum at an angle of attack of 2 degrees. Maybe if it was 4. Okay, so the most correct answer is this. We have lift. Lift is created by pressure differential. The point of minimum static pressure on a positively cambered airfoil flying at a low subsonic speeds at a positive angle of attack is on the upper surface where the speed is the highest. Sounds perfect. On the upper surface where the speed is the lowest. Of course not. On the lower surface where the dynamic pressure is lowest, or on the lower surface when the dynamic pressure is highest. Of course, we eliminate these two. Of course, positive angle of attack, positively cambered. On the upper surface where the speed is the highest. Okay, so when we have the highest speed, we have the minimum static pressure, and and the greater pressure differential. The total drag of an airfoil in two-dimensional flow comprises induced drag and form drag. Of course, no, two-dimensional flow. Interference drag and skin friction drag and induced drag, pressure drag and skin friction drag. It's pressure drag and skin friction drag, but come on, nobody calls it pressure drag. It's form drag and skin friction drag. We will see induced drag at the three-dimensional airflow, and it's caused by the span-wise flow, and induced drag is a byproduct of lift. If we have no lift, we have no induced drag, we have only parasite drag. but let's keep this for later on. So it's pressure drag and skill pressure drag. How are the speeds shown in the figure at point 1 and point 2 relative to the relative wind airflow V? Okay, at this is the relative speed of the wind. V1 is 0 because at the stagnation point it's 0, and V2 is the highest speed of all. So V1 is smaller than V2, correct, and V2 is smaller than V, incorrect. V1 is 0 and V2 is higher than V, correct. V1 is 0 and V2 equals V, no, of course no, because here you can see some kind of curveness. And V1 greater than V2, no. So this is the correct answer. Which of these statements about a steady subsonic flow are correct or incorrect? The static pressure decreases and as the streamlines converge. Here we have converging streamlines. This is a really bad figure. I'll try to get better. So pressure static here decrease. So number 1 is correct. And the velocity increases as the streamlines converge. Of course, this is correct too. It got converging streamlines. Dynamic pressure goes up because speed goes up. Correct. Both of them are correct. While increasing the angle of attack, the leading edge stagnation point of the airfoil moves towards the upper side, of course the lower side. We have seen it a lot of times. Let's do this one more last time. Increase angle of attack, relative flow, and moves downwards the stagnation point. Lower side of the airfoil. An airfoil with positive camber at positive angle of attack will have the highest flow velocity on the upper side at the region. An airfoil with positive camber at the positive angle of attack will have the highest flow velocity, of course, on the upper side. On the front, in front of now, at the railing edge, on the upper side, because it's curved and it also has a positive angle of attack. The stagnation point is the point where the velocity of the relative airflow is reduced to 0, sounds perfect, of the intersection of the total aerodynamic force and the curved line, relative to which the sum of all moments is independent of angle of attack, of the intersection of the thrust vector and the curved line. By definition, is where the velocity of the relative airflow is reduced to 0. Plain and simple. I hope you found this class helpful, and I'm looking forward to do the next lesson. Thank you very much.